Good day everyone. I am John Andre Arsumayang and I will be presenting how chemistry plays a major role in one of the inventions in modern construction. The lightweight concrete improved with fibers, bacteria, and nanomaterials for enhanced thermal, strength, and durability properties. Traditional concrete is widely used but suffers from key weaknesses like high density, susceptibility to cracking, limited thermal performance, and long-term durability issues. This new type of concrete is not just lighter, it is stronger, more thermally efficient, more durable, and even capable of healing itself. And at the core of all this improvement is chemistry. Chemistry involves this invention to show how materials interact and how reactions occur inside a concrete. For concrete to be created, cement hydration is the essential chemical process that gives concrete its strength and durability, forming the backbone of modern construction. When water is mixed with cement, a series of intricate chemical reactions take place, resulting in the setting and eventually hardening of the materials. First, we must begin with the chemistry of cement hydration. So, what is the cement hydration? Cement hydration is the chemical reaction between cement and water that causes the mix to set and harden. When water is added, it initiates exothermic reactions, forming a hardened cementitious matrix that binds aggregates together to create concrete. The main products of this reaction are calcium silicate hydrate, or it is called CSH gel, which provides strength, and calcium hydroxide crystals. The cement reacts with water through a series of exothermic hydration reactions that form like the calcium silicate hydrate. It is the primary strength-giving compound and is the essential binder in concrete, formed when cement reacts with water, providing its strength, density, and durability. By interlocking particles at the nanoscale, this complex layered gel has a variable composition of C over S ratio and structure, acting like a microscopic glue, determining concrete's mechanical properties and resistance to environment degradation. And the next is the calcium hydroxide. It is another byproduct of cement hydration, forming 20 to 25% of hydrated cement paste. And it is vital for concrete strength by reacting with pozzolans to create more strength giving CSH gel, but it also gives the high alkalinity with a pH level of 12.4 that protects steel reinforcement from corrosion. Though excessive amounts can lead to issues like sulfate attack or carbonation if not managed. Cement hydration is the chemical process that converts cement and water into a hardened, long-lasting material capable of sustaining structures. Cement compounds dissolve, recombine, and crystallize in a successful of exothermic processes to produce the key products that give concrete its desired qualities. The creation of calcium silicate hydrate provides the majority of concrete strength, hardness, and long-term durability by forming a dense, interlocking nanoscale network that holds particles together. While calcium hydroxide performs a dual role, it improves initial strength development, generates a highly alkaline environment that protects steel reinforcements, and reacts with pozzolans to generate more CSH gel for increased performance. So now let's talk about lightweight concrete. Lightweight concrete has a lower density than conventional concrete due to the use of lightweight aggregates. The introduction of air or aerated concrete, or the absence of the fine aggregates. It is utilized in floor, slabs, walls, and pre-stressed buildings and provides benefits such as lower structural loads, increased thermal insulation, and speedier construction. Lightweight concrete has a lower density than regular concrete, which is produced by using lightweight aggregates such as pumice, expanded clay, or processed polystyrene. Its advantages include lower building weight, better insulation, and simplicity of transporting. However, it is often less strong and more porous, resulting in weaknesses such as reduced CSH networks, rapid carbonation, increased chloride ion penetration, and a proclivity for microcracking due to its internal porosity. To address these shortcomings, advances in chemistry have included fibers, microorganisms, and nanoparticles to improve its strength, durability, and thermal performance. Researchers concentrate on modifying the chemical composition and hydration behavior of lightweight concrete in order to strengthen its microstructure, refine pore characteristics, increase chemical resistance, and improve overall mechanical properties, ensuring its viability despite the inherent problems associated with higher porosity. So let's talk about why researchers modifying lightweight concrete. There are several airspaces in lightweight concrete. These airspaces diminish concrete strength and make it easier for water and chemicals to enter. This can lead to cracking, corrosion, and degradation over time. We may chemically and physically change concrete to address these deficiencies by adding fibers, microorganisms, and nanoparticles. These additives have an impact on the hydration process, microstructure, and the chemical stability of the concrete. So now, let's talk about the roles of fibers in lightweight concrete. First and foremost, fibers are thin, strand-like elements that are mixed into concrete to improve its structural performance. Polypropylene, glass fibers, steel fibers, and natural fibers are examples of commonly used fibers. And now we are gonna talk about chemistry behind fiber reinforcement. Concrete contains calcium hydroxide and other alkaline hydration products, resulting in a strong alkaline environment. The pH level ranges about 12 to 13. While this high pH prevents steel reinforcement from corrosion, it can injure some fibers. For example, the glass fibers are extremely susceptible in the absence of protective coatings. In such alkaline conditions, hydroxide ions attack the glass silica network, causing it to break down and eventually lose its tensile strength. This degradation causes fiber embrittlement, which weakens the reinforcement function they were designed to serve. To address this issue, chemistry plays a central role in engineering fibers that are stable in alkaline environments. Two major strategies are used. The first one is the alkali-resistant glass fibers. So, what is the alkali-resistant glass fibers? It is loaded with the zirconia and utilized as secondary reinforcement in a concrete to increase durability and strength while preventing deterioration from the extremely alkaline cement environment. They increase tensile or flexural strength, impact resistance, and cracking resistance, allowing for thinner, lighter concrete products such as ornamental panels and pipes, and can replace steel in some applications because of their non-corrosive. High-strength qualities allows glass fibers to live for decades within concrete. So the next one is the polymer-based fibers. Chemically resistant fibers include polypropylene, polyethylene, polyvinyl alcohol, and basalt. Furthermore, Polymer-based fibers in concrete serve as secondary reinforcement, significantly improving crack control, impact or abrasion resistance, ductility, and freeze-throw durability, making it ideal for industrial floors, pavements, shotcrete, and tunnels while reducing corrosion issues when compared to steel. These fibers improve cohesiveness, reduce segregation, and increase fire resistance. But they do not replace main structural steel. Instead, they complement its performance and offer value in specific applications. These fibers are non-reactive in high pH level, flexible and durable, with the ability to preserve tensile qualities even after long-term exposure. Because these fibers do not degrade, these chemically designed fibers can continue to function throughout the life of the concrete. These fibers essentially serve as a first line of defense, ensuring the chemical integrity of the concrete from within. Fibers can play an important role in safeguarding concrete due to their alkali-resistant chemistry and crack-controlling processes. Concrete becomes more durable, chemically stable, and better equipped to withstand long-term environmental degradation when fibers are engineered to not disintegrate in high pH level and to minimize crack propagation. And now, we will talk about the role of bacteria in lightweight concrete. One of the most outstanding developments in concrete is the employment of bacteria. The idea is to make concrete that can mend itself when cracks appear. The bacteria's primary role in concrete, known as bioconcrete, is to self-heal cracks by producing limestone or calcium carbonate. When activated by water entering fissures, preventing corrosion and extending infrastructure life, making it a sustainable solution that improves strength and durability. Scientists employ germs known as Bacillus species. These bacteria produce a naturally occurring mineral called calcium carbonate, which is found in limestone and seashells. These bacteria are encapsulated with nutrients such as calcium lactate, and when combined with this mineral, they heal cracks and restore the structural integrity of the concrete. And now we will talk about the chemistry behind the bacterial self-healing. In bacterial self-healing concrete, bacteria are added in spore form, allowing them to remain dormant inside the matrix until water enters through developing cracks. Once activated, these spores germinate in the presence of moisture and oxygen, consuming embedded nutrients such as calcium lactate and converting them into calcium carbonate, which fills and seals cracks up to about 0.46 millimeters wide. This natural biomineralization process significantly reduces the concrete's permeability, improves resistance to acids, and protects steel reinforcement by preventing corrosive agents from entering. Because the concrete can repair itself, its service life is extended. Maintenance is minimized, and the need for raw materials and carbon-intensive repairs is reduced, making bacterial concrete an environmentally friendly solution for critical structures like tunnels, bridges, and highways. This chemical self-healing mechanism makes concrete far more durable and reduces maintenance costs. Through chemistry, the concrete repairs itself without any human intervention. When water enters a crack in the concrete, it activates the dormant bacterial spores, allowing them to begin a biochemical reaction using calcium lactate as their food source. In the presence of oxygen, the bacteria oxidize the calcium lactate, breaking it down into calcium ions, carbon dioxide, and water. Inside the highly alkaline concrete environment, the released calcium ions react with the carbon dioxide to form calcium carbonate, a solid mineral similar to natural limestones. These calcium carbonate crystals gradually grow and fill the rock, effectively sealing it from the inside. Through this process, the bacteria turn a simple nutrient into a strong, rock-like material that restores the concrete's structural integrity and prevents further damage. We will proceed talking about the nanomaterials in lightweight concrete. The nanomaterials such as nanosilica, carbon nanotubes, graphene, and nanotitanium dioxide are transforming modern concrete by improving both its microstructure and long-term performance. Because these materials are extremely small, often measured in nanometers, they can penetrate and fill the tiniest pores within the cement matrix. This leads to a denser, more refined microstructure, reducing porosity and blocking pathways that allow water, carbon dioxide, and chloride ions to enter. As a result, concrete becomes far more durable and chemically resistant. Nanomaterials also enhance mechanical performance by acting as nano-reinforcement, bridging microcracks and preventing them from growing, which boosts compressive, tensile, and flexural strength of the concrete. Different nanomaterials provide different benefits. Nanosilica reacts with calcium hydroxide during the hydration to form additional CSH gel, the main strength-giving compound in concrete, resulting in a stronger and more cohesive matrix. Carbon nanotubes are exceptionally strong and stiff, allowing them to bridge microcracks and significantly improve toughness, ductility, and crack resistance. Graphene oxide increase strength, reduce permeability, and improve bonding between hydration products because of their large surface area and chemical reactivity. Meanwhile, nano-titanium dioxide provides photocatalytic properties. When exposed to sunlight, it helps break down pollutants and organic matter on the concrete surface, giving the material self-cleaning and air-purifying abilities. Together, these nanomaterials not only make concrete stronger and long-lasting, but also enable the development of smart infrastructure capable of self-cleaning, self-sensing, and potentially even self-healing when combined with other technologies. This marks a significant step toward high-performance, sustainable, and intelligent construction materials for the future. So now let's focus on nanosilica, one of the most widely used and effective nanomaterials in concrete technology. During normal cement hydration, a significant amount of calcium hydroxide is produced. While not harmful, calcium hydroxide does not contribute much to strength and can even make concrete more vulnerable to chemical attack because it is relatively weak and easily dissolved by acidic or aggressive substances. Nanosilica improves this situation through a pozzolanic reaction. Because of this extremely small particle size and high surface area, nanosilica is highly reactive. When it comes into contact with calcium hydroxide, it rapidly reacts to form additional CSH gel, the primary strength-giving base in concrete. This transformation is chemically important for several reasons. It consumes calcium hydroxide, reducing weak areas in the microstructure. It produces more CSH gel, increasing the amount of the strongest and most stable binding material in cement. It refines the pore structure, making the concrete denser and less permeable. It improves resistance to water penetration, chloride attack, carbonation, and chemical deterioration. By increasing both the quantity and quality of the CSH praise, nanosilica significantly boosts concrete's mechanical strength, durability, and long-term performance. The resulting material is stronger, more compact, and better protected against environmental damage, demonstrating how nanotechnology can dramatically improve concrete chemistry. So now let's talk about how all these additives work together in the lightweight concrete. The fibers, bacteria, and nanomaterials each play a vital role in enhancing the performance of lightweight concrete, compensating for its naturally higher porosity and lower strength compared to normal concrete. When incorporated correctly, these advanced materials significantly improve the concrete's mechanical durability and functional properties, though they may slightly reduce workability due to increased viscosity and particle interactions. Fibers such as polypropylene, basalt, or alkali-resistant glass help lightweight concrete resist cracking by bridging microcracks and distributing stresses more evenly. This leads to notable improvements in flexural strength, tensile capacity, impact resistance, and toughness, which are especially valuable since lightweight aggregates tend to weaken the matrix. Bacteria used in self-healing concrete provide a unique advantage. When cracks forms and water enters, bacterial spores activate and produce calcium carbonate, sealing cracks automatically. This biological repair mechanism reduces permeability, protects steel reinforcement from corrosion, and minimizes long-term maintenance. For lightweight concrete, which is more vulnerable to cracking due to its porous structure, this self-healing ability greatly improves durability. Also, the use of nanomaterials such as nanosilica, carbon nanotubes, graphene, and nanotitanium dioxide enhance the microstructure at the nanoscale. They fill microscopic pores, react with hydration byproducts, and increase the formation of strong CSH gel. As a result, nanomaterials make lightweight concrete denser, stronger, and more chemically resistant, with better performance in freeze-thaw environments, chloride exposure, and carbonation conditions. Overall, the integration of fibers, bacteria, and nanomaterials transforms lightweight concrete into a more durable, resilient, and high-performance material, suitable for modern construction applications. Each modification targets different weaknesses of lightweight concrete, and when combined, they create a synergistic upgrade that significantly improves structural reliability and sustainability. In today's world, infrastructure failures are costly and dangerous, and traditional concrete is prone to cracking and long-term damage. Lightweight concrete enhanced with fibers, bacteria, and nanomaterials offer a durable, sustainable solution by extending the lifespan of structures from about 50 years to over 100. Through improved crack resistance, a denser microstructure, and self-healing capabilities, this technology also reduces maintenance costs by up to 50% as bacteria seal cracks and before harmful substances can cause further damage. Additionally, Nanomaterials like nanosilica strengthen the concrete while reducing cement usage, lowering carbon emissions and minimizing the need for reconstruction. Its lightweight nature cuts transportation energy and its enhanced resilience allows buildings and bridges to better withstand earthquakes, harsh weather, and chemical attack. Altogether, this advanced concrete supports sustainability, improves safety, and enable the development of stronger, smarter, and more efficient future cities. In overall, this innovation of lightweight concrete enhanced with fibers, bacteria, and nanomaterials show how deeply chemistry shapes the future of construction by overcoming the natural limitations of lightweight concrete. Its porosity, reduced strength, and tendency to crack through chemical and structural improvements at the micro and nanoscale. Fibers provide mechanical reinforcement by bridging cracks. Bacteria reduce a self-healing chemical process that restores integrity. And nanomaterials create more CSH gel for a denser, stronger matrix, all working together to form a lighter, more resilient, and more sustainable material. This advancement has real-world impact as it reduces repair costs, increases safety, extends structural lifespan, and lowers carbon emission by minimizing reconstruction. As urbanization and environmental challenges grow, chemistry-driven improvements in lightweight concrete offer a smarter, greener, and more efficient foundation for future infrastructures, proving that by mastering the chemistry in concrete, we can build structures that are durable, functional, and aligned with society's evolving needs.